Hi, hello dear students. Welcome to physics class of PU2. We have been discussing about the chapter nuclei. In the past few classes regarding the chapter nuclei, we have discussed about the introduction part, then Einstein's mass energy equivalence relation. Einstein's mass energy equivalence relation we have discussed, and what is mass defect, then what is binding energy per nucleon or specific binding energy, and also we have solved certain important numericals based on the calculation of the mass defect, binding energy and specific binding energy or binding energy per nucleon. And also in the previous class we have discussed about the binding energy curve. You all know that what is the binding energy curve. The binding energy curve, it is the graphical representation of what? The variation of the binding energy per nucleon, versus atomic mass number of different nuclei. So that graph, that is binding energy per nucleon versus the atomic mass number. So this one we have discussed in the previous class. So what is the importance of the binding energy per nucleon versus atomic mass number curve, right? So you all know that the binding energy per nucleon is more for a nucleus which is having the binding energy per nucleon is more, then that nucleus is more stable. So the maximum value of binding energy per nucleon, then the stable is the nucleus. The nucleus is more stable, right? So in case of binding energy per nucleon, we have seen that the binding energy per nucleon versus atomic mass number curve, we have seen that the heavier nucleus, they try to split up and to become a lighter nuclei and to become a more stable. And also in the lighter nuclei region, they try to combine with the lighter nuclei combine to form a heavy nucleus, and again they try to become a stable, right? So that is what we have discussed in case of what the binding energy curve, binding energy per nucleon curve versus the atomic mass number of different nuclei. So based on this binding energy curve, we are going to explain here the two important processes. Right? The two important processes are what here? The nuclear fission and the nuclear fusion. After discussing this, we are going to distinguish between what? The nuclear fission and nuclear fusion. So what is a nuclear fission? The process in which a heavy nucleus splits up into two lighter nuclei of comparable masses with the release of 2 or 3 neutrons and a large amount of energy. So it is a nuclear reaction we are going to write here. What happens in this case? So from the binding energy curve, what we have obtained is for an atomic mass number of greater than 230, right? For an atomic mass number greater than 230 or 240, around this region, right? The atomic mass number of greater than 230 or around this region the binding energy per nucleon is small. So if the binding energy per nucleon is small, then that nuclei is unstable, and it try to become what? The stable nuclei. For this reason, what happens? These atomic mass number of greater than this, they try to become a stable, and what happens in that process, right? The heavy nucleus splits up into two lighter nuclei, right? Two lighter nuclei of comparable masses with the release of 2 or 3 neutron, and also there are large amount of energy is released in this process. So here one example we can see about the when uranium 92-235 it is bombarded with a neutron, right? Then a neutron is captured by the uranium 92-235. Then it goes to a unstable state, that is 92 uranium 92 236. So one neutron is captured from this uranium 92 235. Then it goes to this state, that is an unstable compound nucleus is formed, that is what, 92 236. Right? Atomic mass number is increased by 1 unit when one neutron is captured by uranium 92 235. After this unstable, a star indicates what it is unstable. Then it tries to become stable after splits up into what, two lighter nuclei. So here the barium and krypton, two lighter nuclei of comparable masses are formed. So here barium 56 is its atomic number and 141 is its atomic mass number. Again krypton 3692. Again three neutrons are released in this reaction, and a large amount of energy is released in case of your nuclear fission. Here if you calculate the what, how we are going to calculate the amount of energy released in this reaction, right? We are saying here the large amount of energy is released. So the large amount of energy is released here. So for that we are going to calculate here the mass of the reactants and the mass of the product. So that one, what I given the calculation of mass defect in the previous class. I have given this example to calculate the mass defect. So the masses of the reactants are given and the masses of the products are given in terms of AMU. Then you have to calculate the mass defect. Then by multiplying 931 MeV, you will get the amount of energy released here. Right? So if you done the calculation of total mass of reactants, minus total mass of products, so what we have got in the calculation is, that is equal to around what we have got is that is about 200 mega electron volt energy is released. That the difference in the masses is about 0.216 AMU. If you done the calculation of the mass of the reactants and the mass of the products, barium, krypton and tritium, so the masses of the reactants minus the masses of the products, we have done the calculation. We are getting here some missing mass. So whatever we are getting the missing mass here, 0.216 AMU amount of mass is lost here. So this example we can give as the instant mass energy equivalence relation. Whatever the amount of mass is lost here, that is converted into energy. Now we can calculate here 0.216 into 931 mega electron volt. This is around, you will get what, 200 mega electron volt. Right? A large amount of energy is released here, that is 200 mega electron volt. 200 mega electron volt, it is a large amount of energy. So in a nuclear fission reaction, right, the nuclear fission reaction is what? The process in which a heavy nucleus is a heavy nucleus, right, and it splits up. Why it splits? To attain the stability. It splits up into two lighter nuclei of comparable masses. Lighter nuclei are formed here. These are also called as what? The fragments, right? The fragments are obtained here. These are also called as what? The daughter nuclei, right? These are also called as what? The fission fragments we can call it, right? These are also called as what? The daughter nuclei. So barium 56, 141, krypton 36, 92. 3 neutron and large amount of energy is released. So this energy came from what? The mass difference what we are getting. The mass of the reactants minus total mass of the products. So mixed mass is what? Whatever the amount of mass we are getting, this is having the less mass, products mass is less and reactant mass is large, right? So 0.216 AMU amount of mass is lost here. That is converted into energy, that is around 200 mega electron volt. And this energy is released in the form of the kinetic energy of this fission fragments. Whatever the fission fragments we have here, that is barium, krypton and neutron. So it appears in the form of the kinetic energy of these fragments, and also sometimes it may appear as what? The heat energy or light energy. In this way also it may appear. This energy appears in the form of the kinetic energy of these fission fragments, or also this energy appears in the form of light or heat energy, right? So this is about the nuclear fission. Now next point we are going to see is about what is nuclear fusion. Fission, it means what? Splitting, right? And nuclear fusion means what? It is combining, right? ಇಲ್ಲಿ combine ಆಗುತ್ತೆ, ಇಲ್ಲಿ ಏನಾಗುತ್ತೆ? Split ಆಗುತ್ತೆ. So in case of nuclear fusion, what happens? It is the process in which two or more lighter nuclei combine to form a heavy nucleus. So from the binding energy curve we have obtained here, the lighter nuclei, those nuclei is having what? The binding energy per nucleon is small. Right? Binding energy per nucleon is small, so that if the binding energy per nucleon is less, they try to become stable. That means what? These lighter nuclei combine to form a heavy nucleus, right? So if the atomic mass number is less than 10, these nuclei are what? Their binding energy per nucleon is small, and they try to become stable by combining with another lighter nuclei, and they form a heavy nucleus with stable nuclei with the release of large amount of energy. So here I have given one example. So you all know that the hydrogen, 1H1 is hydrogen, 1H2 is deuterium, 1H3 is tritium. So these are the isotopes of hydrogen. Now here I have taken an example of 1H2 and 1H2. Two deuteriums are combined to form helium-24, right? So helium-24, again a large amount of energy is released here. This is the process in which two or more lighter nuclei combine to form a heavy nucleus with the release of large amount of energy. So here the process nuclear fission and nuclear fusion process that takes place mainly to attain the stability. That is the important point. To attain the stability, the nuclear fission takes place and nuclear fission processes takes place. So 1H1 is hydrogen, 1H2 is deuterium. Two deuterium nuclei are combined to form a helium-24 with release of large amount of energy. So again here one more important point here. To occur this process, high temperature is required. High temperature of the order of 10 to the power 9 Kelvin is required, because here we are going to combine. Here there is a what is the process takes place here? It is the combination process. Here the two lighter nuclei are going to combine here. So 1H2, here nucleus is also positive, and here 1H2 is also its nucleus, positive charge nucleus here. So there is a repulsive force between the two nuclei, right? There is a repulsive force between the two nuclei, so it is a difficult process to combine the two lighter nuclei and to form the heavy nucleus. So for that reason, what takes place here? The 10 to the power 9 Kelvin of the order of 8-9 Kelvin order of temperature is required. When this process takes place at the order of 10 to the power 9 Kelvin temperature, this nuclei is having that this nuclei gets the large amount of kinetic energy to overcome the repulsive force. So this process nಮಗೆ large amount of temperature ಬೇಕಾಗುತ್ತೆ of the order of what 10 to the power 9 Kelvin. ಯಾಕೆ ಇಷ್ಟು amount of temperature ಬೇಕಾಗುತ್ತೆ? So here ಇಲ್ಲಿ ನಾವು ನ್ಯೂಕ್ಲಿಯೈ ಅನ್ನು ಕಂಬೈನ್ ಆಗ್ತಾ ಇದ್ದಾರೆ. ನ್ಯೂಕ್ಲಿಯೈ ಕಂಬೈನ್ ಆಗಬೇಕಾದ್ರೆ ಅಲ್ಲಿ ರಿಪಲ್ಸಿವ್ ಫೋರ್ಸ್ ಇರ್ತದೆ. ಆ ರಿಪಲ್ಸಿವ್ ಫೋರ್ಸ್ ಅನ್ನು ಓವರ್ಕಮ್ ಮಾಡಿ ಅವೆರಡು ಏನಾಗಬೇಕ್ರಿ? ಕಂಬೈನ್ ಆಗಬೇಕು. ರಿಪಲ್ಸಿವ್ ಫೋರ್ಸ್ ಅನ್ನು ಕಂಬೈನ್ ಮಾಡೋದ್ರ ಸಲುವಾಗಿ ಈ ಆರ್ಡರ್ ಆಫ್ ಟೆಂಪರೇಚರ್ ಅನ್ನು ಮೇಂಟೈನ್ ಮಾಡಿದಾಗ ಆಫ್ ದಿ ಆರ್ಡರ್ ಆಫ್ 10 to the power 9 Kelvin ಟೆಂಪರೇಚರ್ ಅನ್ನು ಮೇಂಟೈನ್ ಮಾಡಿದಾಗ ಏನಾಗುತ್ತೆ? ಸೊ ದೀಸ್ ನ್ಯೂಕ್ಲಿಯಸ್ ಗೆಟ್ಸ್ the high amount of kinetic energy to overcome that force. So that is the reason for what getting requiring of what the high temperature of the order of 10 to the power 9 Kelvin. Again helium-24 is formed. After this process, this is the product we obtained. Again the amount of energy released is what 24 mega electron. If you compare the nuclear fission reaction, the amount of energy released per nuclear fusion is small, but if you calculate the amount of energy released per nucleon is large in case of nuclear fission. Now let us discuss those also. What the difference between the nuclear fission and nuclear fission reaction. So in that case we will discuss all them. Right, now let us discuss about the difference between the nuclear fission and the nuclear fission. I think this point is clear. What is nuclear fission and what is nuclear fusion? Nuclear fission is what? The process in which a heavy nucleus splits up into two lighter nuclei of comparable masses with the release of large amount of energy. It is a splitting process. The fission is a splitting process and nuclear fusion is what? Combining process. It is a process, fusion is a process in which two or more lighter nuclei combine to form a heavy nucleus, again with the release of large amount of energy. So examples for each case is given. Right? Now again we have to discuss here what the difference between nuclear fission and nuclear fusion. Now, what are the important difference between the nuclear fission and nuclear fusion? So, in the examination, you get a question of 3 mark or 5 mark. Write the difference between or distinguish between nuclear fission and nuclear fusion. For 3 mark, you have to write 3 difference, and for 5 mark, you have to write 5 difference. Right? So, here the one difference you can write the definition of nuclear fission and nuclear fusion, and second one you can write the examples. Now let us see the next difference between the nuclear fission and the nuclear fusion. Right? So first one, what you have to write here, the definition and the examples. Next, second. So as you have seen, the nuclear fission reaction, the energy released in the uranium nuclear reaction is about 200 mega electron volt. And here is of the order of 24 mega electron volt. So second difference what you can write here, that is in terms of energy released. Energy released per fission is large. Energy released per fission is large. So energy released per fission reaction is large here. Energy released per fission reaction is large. And in case of nuclear fission, energy released per fusion is small. Energy released per fusion is small. So here of the order of per nuclear fusion reaction, the amount of energy released is 24 mega electron volt, around this okay. But here in case of nuclear fission, it is of the order of 200 mega electron volt. So per fission is energy released large, per fusion energy released is small. Now the next difference you can write the energy released per nucleon. So here 200 divided by, so its atomic mass number if you divide, so very small amount of energy you will get. So it is 0.20, right? But here in case of 24 divided by its atomic mass number, here it is what? 4 if you. So total number of nucleons if you consider, here it is 4. Here total number of nucleons if you consider is 230. So energy released per nucleon is small. Sorry, here in case of nuclear fission is small, right? Energy released per nucleon is small. So in case of nuclear fission reaction, the energy released per nucleon is small or it is less, right? But in case of the nuclear fission reaction, 24 divided by 4, it is of the order of 6 mega electron, very large. So energy released per nucleon is large in case of nuclear fusion reaction. Energy release per fission is large, energy release per diffusion is small. Energy release per nucleon is less and small, energy release per nucleon is large. Okay, so nuclear fission reaction. Next, fourth difference. So as we have seen, high temperature is required here in case of nuclear fusion reaction. The high temperature is not required in case of fission reaction. High temperature is not required. So for nuclear fission reaction, high temperature is not required. So this can take place at ordinary temperature. The nuclear fission reaction can take place at an ordinary temperature, but in case of the nuclear fission reaction, high temperature is required. High temperature is required of the order of high temperature is required of the order of 10 to the power 9 Kelvin is required. Again, the next difference we are going to write here. It can be controlled. It is a controlled reaction. It can be controlled and it cannot be controlled. So nuclear fission reactions can be controlled. So we have the nuclear reactor, right? Nuclear reactor, their controlled nuclear chain reactions are takes place, and a large amount of energy is released. That is, the nuclear fission reactions takes place. It can be controlled, but it cannot be controlled. So why? So high temperature of the order of 10 to the power 9 Kelvin is required. So that large amount of temperature is present on sun and stars. So these reactions are takes place at sun and stars because of on which the high temperature of the order of 10 to the power 9 Kelvin is required, that is present there. So that's why these reactions, nuclear fusion reactions, these nuclear fission reactions are also called as what? The thermonuclear reactions, because of what? High temperature is required and it cannot be controlled there, because they takes place at sun and stars at which the high amount of temperature is present. So that's why these reactions are also called as nuclear fusion reactions, are also called as what? Thermonuclear reactions, and the energy released here is called as thermonuclear energy. So that's why this can be controlled and it cannot be controlled. And one more important difference is the end products are harmful in case of the nuclear fission reactions. So end products, what we are getting here, they are harmful. End products are harmful. So whatever the end products we are getting in case of nuclear fission reactions, they all are what? Usually radioactive, and hence they emit the alpha beta radiations. So that's why these end products are harmful. That what we are getting in case of nuclear fission reactions. Here the end products are not harmful. End products are not harmful, and there is no nuclear wastage, and here we are getting the nuclear wastage. End products are not harmful. Right. Again, you can write the difference here. The nuclear fission, it is the principle of atomic bomb. It is the principle of atomic bomb, and the nuclear fusion, it is the principle of hydrogen. It is the principle of hydrogen. So the large amount of energy released in case of nuclear fission reaction, may be used for the constructive purpose as well as destructive purpose. So destructive purpose, if you can consider, it is an example of atomic bomb. Nuclear reactor, it is constructive purpose, nuclear reactor. So there also we can produce the energy. Again, it is the principle of hydrogen bomb, nuclear fusion. And again, you can, last difference what you can write here, the neutrons are the link particles. Neutrons are linked particles, and here the protons are linked particles. So how these nuclear fusion reactions continues? Based on the protons link the one reaction to another reaction, so that's why protons are the link particles. Yep, in case of nuclear fusion, and in case of nuclear fission, whatever in the products, the two or three neutrons are released in nuclear fission reactions. Again, these neutrons continue the next nuclear fission reactions. So in this way, chain reaction continues. So these neutrons again can carry what? The next nuclear fission reaction. So that's why neutrons are the link particles here, and the protons are the link particles in case of nuclear fusion reactions. So with this important difference between the nuclear fusion. So with the important that is with the definition, examples, and difference between the nuclear fission and the nuclear fusion. So I think it is very important point. It is clear to you all. In the next video class, we will continue the next one. Okay, so thank you.